Hello friends, welcome back to the tetrahedron chemistry classes. Guys, in today's class I am going to discuss mass spectral interpretation of the ethers. Actually, one of my subscriber said 3 or 4 days back commented in my mass spectrum lecture where no one explained ethers. So I am going to explain the mass spectral interpretation ether for him as well as for my other subscribers, right? So it is from the heading it is already clear that I am going to discuss your mass spectral interpretation of ether, right? But sometimes if you don't have any idea about what the compound is, so you in that case you may have the question in this form in which I have written on the slide, right? Compound with the molecular formula C4H10O shows a band at 1130 centimeter inverse in its IR spectrum. Deduce the structure of the compound consistent with the given mass spectrum, right? For time being you can forget about this heading which I have written over there and you only think about this particular question, right? So whenever this IR spectrum is given for any compound, then you may have a fair idea about the functional group present in the compound, right? Here in that case it clearly states that near 1130 centimeter 1130 centimeter inverse you are getting a band, and when you have your ethers, right? So this carbon single bond oxygen basically it gives band in the IR spectrum in this particular range 11 to 1150 centimeter inverse. So it is clear from this, that means this particular compound is having this C single bond O linkage, right? This is first job which we have to done. Once you did this, then what you can do, you can go for the solution, right? So now you are having the writing solution. Now you have clear idea that you are having the carbon single bond oxygen in it. So what you can do, you can put your oxygen in the center and then connect the carbons present in it, right? So this is how I am connecting. So this is your CH3, okay, and this is your CH2, and this is your CH3, and this is your CH2. So this is your diethyl ether. So I can write the name of this particular structure. It is diethyl ether, right? It is general name, and IUPAC name is ethoxyethane. But another possible structure for this particular molecular formula is this CH3O CH2 CH2 CH3, right? This is your methoxypropane or methyl propyl ether, right? So you can write like that. Only these two possibility or only these two possible structures are possible for this particular molecular formula. It is consistent, right? These two structures are consistent with this molecular formula. You can count 1, 2, 3, 4. 4 carbons are there. Then 3 to 5 to 7 to 3, 10. 10 hydrogens are there and 1 of the oxygen, right? Since the second one is the isomer of the first one, so these two have the same molecular formula. But you have to decide whether the correct structure for consistent with this particular mass spectrum is this one or this one. So please remember, I am going to discuss very important thing here. First of all, you should know what kind of fragmentation pattern or what kind of the cleavage are there in case of the ethers. So you will remember this particular point. In that case, you see alpha cleavage is very common in that case, right? Alpha cleavage, and apart from this alpha cleavage, beta cleavage is also there. And ethers generally have very low abundance molecular ion because it readily gives by the fragmentation pattern a more stable ion. That's why sometimes you may not find your molecular ion peak in that case. But in this particular example, you have been given that 74 is the molecular ion peak, and then you are having the other three significant peaks in that case, 59, and 45 and 31. These are the M by Z values. Okay, so how we can interpret or how we can do the things in that case. So straightforward I am jumping to the conclusion in that case because I don't want to waste too much of time, right? That's why I am taking that particular example which is consistent with this mass spectrum, and later on I'll throw a little light on the other structure which is not possible, right? So what we can do here, we can write this particular compound CH3 CH2O CH2 CH3, right? You know this oxygen is having 2 lone pairs on it, and when you do the mass spectrometry, you will bombard this molecule with the 70 electron volt electron, so which will eject, basically this high energy electron will eject one of the electron present on the oxygen atom. Please remember, loosely held or the loosely bound electron will be knocked out first from the system if it is present in the system, and in this system you are having the lone pairs, that means loosely bound electron, so it will be easily knocked out by the 70 electron volt electron. Okay, and then you will have this particular thing. This is your CH3 CH2 oxygen, 2 electrons are there, one is knocked out by the 70 electron volt electron, and then you are having CH2, and then you are having the CH3, and of course plus 2 electrons. Okay, one electron is this one, other one is coming from this particular oxygen. So basically this is your molecular ion. Okay, please remember, this is your molecular ion. And when it is the molecular ion, so what you can do, you can take the molecular weight of it, of this particular thing. Okay, so if you count the carbon, 1 2 3 and 4 carbons are there, it simply means 12 into 4, that will give you 48, and then 10 of the hydrogens are there, so 10 into 1, that will give you 10, and then 1 of the oxygen is here, so 16 into 1, that will give you the 16. Okay, and entire molecular weight would be 74. So this will have the M by Z value of the 74. Let's check whether it is there or not. If I go back, then you can clearly see your molecular ion peak is at M by Z 44. This is how you can prove that this 74 ion is there with the help of that molecular ion. But this 74 will also be there in the second case as well, right? Because it is also having the molecular weight of 74. So this molecular ion peak cannot actually decide whether the compound is the first one or the second one, right? Now coming back again, so this is the structure. I already told you the very famous fragmentation patterns in that case is the alpha cleavage. So I am doing here alpha cleavage. Alpha cleavage. So what is the meaning of the alpha cleavage? That means the bond at the alpha position to the oxygen will break. So if you see here, this bond is the alpha bond, this bond is the beta bond. Similarly, this bond is the alpha bond, this bond is the beta bond. So if you are doing your alpha cleavage, so you can break either this bond or this bond, since both are the methyl groups, right? This is methyl, this is also this is methyl, this is ethyl, this is also the ethyl. So whether you do or you break this right hand side bond or the left hand side bond, this will not make any difference to the results, right? So what I am doing, I am breaking this bond, say from here. So homolytic cleavage will occur, and one of the electron from this bond will go to this carbon atom and another will come onto this particular oxygen atom. So what it will result? So it will result this particular species, say CH3, CH2, my oxygen now, okay, and this oxygen is now having 2 of the lone pairs with a positive charge plus CH2, CH3 and dot radical. Okay, this is another ion, right? This is another fragment ion, and this fragment ion will have the m by z value of what? 2 carbons. See, this is your ethyl, carbon and carbon. 12 into 2, that is 24. 24 or 5 is your 29. 29 and 16. If you do here 29 and 16, so that will give you the 45. So this is having the m by z value of the 45. That means you will have the peak at the m by z value of the 45 in the mass spectrum of the diethyl ether. Let's go back and check whether it is present or not. Yes, this 45 peak is there, right? But if you do the cleavage of this particular species, right, so this will not give you this 45 m by z value. So this second structure cannot be your answer. First structure is actually your answer, and we will also see the other possibilities in these two structures, which will prove that only the diethyl ether is the probable structure for this particular given spectrum. So far I have explained m by z 74 and m by z 45. Now let's discuss the another thing. Say I am writing this structure again. So I need some space. So what I am doing here, I am removing it. Okay. And then I am writing this molecular ion again. CH3, CH2, oxygen, this is CH2, this is CH3, and I have already produced my molecular ion in that manner. Now I am going to do the beta cleavage. Okay, here I am going to do the beta cleavage. So I am writing beta, CLEAVAGE. This is your beta cleavage. So beta bond, see, this is the alpha bond, this is the beta bond, this is alpha bond, this is again the beta bond. Now I am going to break this beta bond. So when you break this beta bond, what will happen? One of the electron will come here, okay, and one will go onto this carbon atom, and one will come from here to here. Okay, so what you will have? You will have minus of CH3, that means methyl radical, and after methyl radical you will have this species, which is your CH3, CH2, single bond oxygen, one lone pair, one positive charge, and double bond CH2, right? I am having this particular species. How I am producing this species? See, you know, for the formation of the one bond you will always require pair of electron. So one electron is coming from this fragmentation pattern, and one odd electron is already there, which is coming here making a double bond. Now only positive is there. Okay, if you count the weight or the molecular weight of this particular ion, so you can see 3 carbons are there. So 12 into 3, that will give you 36. Okay, and then you are having the 7 of the hydrogens. So 1 into 7, that will give you 7 again, and 1 of the oxygen is there. So you can write 16 into 1, that will give you 16. If you add all together, 6, 6, 12, 12 or 7, you are 19, okay, and carry 1, that is 59. So this species is having m by z value of 59. Let's check whether this particular ion is present in the spectrum or not. So if I go back, then I clearly find this m by z 59 value, okay, and further you can verify this ion is basically resonance stabilized, right? If it is resonance stabilized, then you can easily draw the resonance structure of this one. What can happen? The electron pair can come here, and then you end up with another structure, which would be your CH3, this is CH2, this is O with 2 full lone pair on it, and this is CH2 positive, right? Since this is resonance stabilized, that's why you can see here its intensity is also quite good here, right? It is more than molecular ion, it is more than your fragment which is giving the M by Z value at 45. This 59 is quite abundant due to this resonance, right? But what about this 31? This is the base peak. If you know the basics of the mass spectrometry, so peak which is having nearly 100% of the abundance or the intensity is known as the base peak. So this is your base peak. So how this base peak is coming, it is something very, very important which you need to understand. And here you will look for your other cleavage, right? So how this cleavage will occur, let's see. Let's go back. Okay, now I see, okay, I need some space. So what I can do, I can remove this part from here. Completely I can remove this part. Okay, and now the explanation of that thing. So I am writing with the blue here. So how it is producing. So you have already produced this particular ion, right? And from this particular ion you will get your 31, peak at 31. So what I am doing, I am doing this, I am drawing this again. So this CH3 is here, so I am writing this CH3 in that manner. This is just for the sake of explanation. This is H, this is H, and then you are having CH2 here, okay, and then you are having, say, oxygen, double bond, CH2, and your dot and positive. So how actually I am producing this particular ion? This is something very, very interesting and very, very important. Okay, so what will happen, you know, this hydrogen is there. So what will happen, this bond actually will break. One electron will go there, and simultaneously this will also break. One electron will go there, okay, and one electron will come here. So this hydrogen along with the one electron will add to this oxygen atom, and then you are having this particular fragment, CH2 double bond CH2. Let's verify again how I have produced this particular ethylene as a neutral molecule, right? So this bond is there. So this CH3 bond, which is this one of the hydrogen, whether this one or that one, this bond will break, and one of the electron will go here, and one hydrogen along with the one electron will add on to this particular oxygen atom, and when this bond cleaves, this will push one electron above, then it will be your CH2 and double bond CH2. Now what you left with is CH2 double bond OH. So another very important fragment is your this one, plus CH2 double bond OH, and of course positive charge is there on the oxygen atom. If you count the molecular weight of this particular fragment, then one carbon is there which is 12, and 3 of the hydrogens are there which is 3, and one oxygen is there which is 16, and that will give you 31. So this is M by Z of 31. So I have explained all the possible molecular ion which are present in the mass spectrum of the diethyl ether. I have explained the 59, I have explained the 31, I have explained the 45, and I have also explained the 74. If I go back, let's verify. See, I have explained this, 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 and this. But one ion is also there which I haven't explained, right, so far. So what is this actually? So please remember, this is actually M by Z of 29. So from where this M by Z of 29 is coming? It is coming from the heterolytic cleavage. See how this heterolytic cleavage had happened in that case. Say for example, you are having this your CH3, and then you are having your CH2, and then your oxygen, this is your CH2, this is CH2, and this is dot positive and 2 lone pair. So in that case, in this particular molecular ion, heterolytic cleavage will occur, okay, and during this heterolytic cleavage, the electron pair will go on to this particular oxygen atom since it is more electronegative, and it will produce this particular species, CH3, CH2, oxygen. One lone pair was already there. One electron pair is coming from this heterolytic cleavage, right? And when it is coming from the heterolytic cleavage and one of the electron was already there on it, so you can write like that, and then you left with what? CH3 and CH2. Okay, this is your CH3, please remember. Okay, and now since this is the heterolytic cleavage, both the shared pair of the electron, this carbon has lost now. So obviously this will have the positive charge on it. So if you put the positive here, so this value is actually M by Z 29. So this is how you can explain the mass spectrum of the your ethers. Now what you can do, you can practice by your own, or if the time permits. Okay, quite time is there. So this is your another structure. How you can explain this particular right mass spectrum if it is the ether, right? So again it is quite simple. You can do your alpha cleavage and the beta cleavage, and then you can decide what is this. So let's discuss this structure as well. So this is what your isopropyl and pentyl ether, isopropyl and pentyl ether. So structure isopropyl, let's make the isopropyl group CH3. I hope you know how to write the isopropyl group. This is isopropyl group, and this isopropyl and pentyl ether, that means oxygen. Pentyl means 5 carbons are there, 1, 2, 3, 4 and 5. Then you can complete the valency, CH2, 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 CH2. So this will produce this molecular ion. I am not doing this extra step here. You know that when 70 electron volt electron will bombard onto this particular compound on this particular sample, then one of the electron present on the oxygen atom will be knocked out that 70 electron volt electron. Okay, this will produce this particular molecular ion. Okay, this is quite simple. Now what you can do, you can take the molecular weight of this particular compound. What is this? Okay, so let's take the molecular weight. How many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons are there. So you can write here 12 into 8, that is 96. Okay. Then you can count your hydrogen, 3 to 5 to 7 to 9 to 11, 12, and 12, 3, 15, 15 and 3, 18. Okay, 18 hydrogens are there. It simply means your 1 into 18, and one of the oxygen is there. So what you can do, oxygen 16 times 1, this will give you the 16. If you add all together, 8 and 6, 14, 14 and 6 are 20, 0, carry 2, 3, 4, 9 or 4, 13, 130. Okay, so this molecular ion is there. Basically it is M by Z 30. So I can write M by Z 30 here. Okay. Now what you can do, you can go for the alpha cleavage. Okay. So first of all, see, this is the very significant one. This 71 is quite significant. So let's discuss this 71 peak first, how it is actually forming in the system. So I'm going for the heterolytic cleavage, right? I'm writing heterolytic cleavage. Heterolytic cleavage. So I'll do the alpha cleavage first. Okay. So this is one alpha bond. This is another alpha bond, and I'm doing the heterolytic cleavage. So for example, I'm doing for this one. Okay, and then I'll do with this one. Two kinds of the heterolytic cleavage. First is this, and second this. Let's say I'm breaking this one. So if I am breaking this one, what will happen? Heterolytic cleavage is happening in that case. So electron pair will go on to this particular oxygen atom. So what you will get in that case? Of course, you will get CH CH3 and CH3, and this carbon will have the positive charge. Okay, and then you are having another fragment which is nothing but your oxygen 1 2 3 4 and extra electron, and then you are having CH2 times 4 and CH3. This is the radical. This will not be detected in the mass spectrometry, but this cation will be detected. And you know, this is what? This is your secondary carbocation. Secondary carbocation. And what is the molecular weight of this secondary carbocation? It's quite easy to you calculate. Okay, so 3 carbons are there. 12 into 3, that is 36. Okay, plus how many hydrogens? 3, 3, 6 and 7. 7 hydrogens are there. That will give you the 43. M by Z value of the 43. Let's check whether this M by Z 43 is there or not. This M by Z 43 is there, and you can see here this is the base peak. This is my base peak, and we know this secondary carbocation is more stable, so it will have more chance to survive and reach to the detector, and its abundance will be quite high, so you are getting this particular peak. Fine, there is no problem in that. But say for example, if you do the cleavage, heterolytic cleavage, from this end actually, right? So what will happen in that case? The second cleavage, say I am using this blue color. Okay, when you do the heterolytic cleavage, so what will happen in that case? This will come here, and then I am writing here you are having this CH3, and then your CH and another CH3, and then oxygen 1 2 3 4 and 1, just like that, and the remaining fragment, which is what your CH2 times 4 and CH3. That means 5 carbons are there. Okay, 5 carbons are there. So 5 carbon means 12 into 5, that will give you 60, and then 8 and 3, 11 hydrogens are there. So 1 into 11, so I am writing 11 here, that will give you the 71. So this is M by Z of 71. So this peak is also there. So I have explained this 43, I have explained this 130, I have explained this 71. However, these two peaks are also there. This 29 is also there, and as well as this 115 is also there. But these two peaks, guys, they are not very much strong. Since they are not very much strong, so what you can do, you can ignore them. But if you want, then actually what is the, from where actually we are getting this 115? So I can explain you from where we are getting. For this, I will write the structure again for you, like that. Say this is your CH3, this is your CH, and then your CH3, right? In that case, I can write, and this is your oxygen, and then the remaining part, this is your CH2 times 4 and then the CH3, and this was your molecular ion, like putting positive over there, these two. Okay, so how actually I am producing this one? Beta cleavage. I will do the beta cleavage for this one. Beta cleavage. So beta cleavage is what? That means 2 beta bonds are there. One beta bond is here and another beta bond is this one. Okay. See, this is your alpha, this is your alpha. Just next to the alpha, this is beta, this is beta. So I can break this bond or this bond. Both will give you the same fragment. Please remember, both will give you the same fragment. So I am breaking it. Say this. So one of the electron will go to this methyl group and one electron will jump here and one electron will come from this particular oxygen atom, and this will produce this particular species, right? CH3 and then the CH, okay, and then you are having double bond here, and then the oxygen with one lone pair and a positive charge, and then CH2 times 4 and CH3, right? This fragment I am getting here, okay? And of course here CH3 methyl free radical will be knocked out. So how many carbons are there in that case? 4, 5, 6, 7, right? 12 sevens are 84. One of the oxygen is here, so 16 into 1, that is 16. Okay, then hydrogens 3, 4 and 3, 7, 7 and 8, 15. 15 hydrogens are there. So what you can do, 1 into 15, that is 15, right? And that will give you 115. So this fragment is basically due to the m by z value of 1 by 15. This fragment is giving you this particular value. Let's go back and check. Yes, this is there actually. This is how you can explain 150 as well. If you want to explain this 29, it is quite obvious again. This is also the easy one, right? But along with this one, this 70, this 43 I have explained, right? But this peak is quite low, 29. What you can do, you can ignore it, okay? Or if you want to do, then you can do by yourself how actually your beta cleavage is happening in that case, or other cleavage. But it is not necessary in the IR spectrum as well as in the mass spectrum to explain each and every bond. If you are able to explain your molecular ion peak and other significant peak, then it will be quite obvious. And of course this is producing somehow with the removal of the ethyl cation C2H5 positive. It is producing due to this one. Okay, so I hope you understood the lecture well. So this is how we can explain the mass fragmentation pattern of the aliphatic ethers. In the next class, I will try to explain the mass fragmentation pattern of the aromatic ether as well. Okay, so if you like the video, if you understood the lecture well, so please like my video. And if you are new here watching video for the first time, please subscribe the tetrahedron chemistry classes and do share with your friends as well. I'll meet you in the next lecture with the mass fragmentation pattern of the aromatic ether. For now, I am signing out. Thank you very much.